Good morning. So today we will study a camera calibration. In previous time, we learned some matching algorithms. How can we extract some meaningful points from multiple images and make some correspondence between them? And the SIFT is some dominant feature and matching, dominant feature for image matching, which is scale invariant feature. And today we will proceed to camera calibration. And there will be two topics, camera calibration and camera localization. Actually, camera localization is a subset of camera calibration. So mostly about camera calibration. In one word, in one sentence, the goal of camera calibration is getting intrinsic and extrinsic camera parameters. We learned intrinsic and extrinsic camera parameters, right? Intrinsic is for 3D camera coordinate system to 2D image coordinate system, like focal length, focal and principal point. That is about intrinsic camera parameters, and extrinsic is for 3D word to 3D cam, like 3D rotation and 3D translation. So we have some, 3D word coordinate system is some canonical or reference coordinate system, and camera coordinate system is defined for each camera, and so that we are going to apply 3D rotation and 3D translation. But there is no ambiguity, just matrix multiplication. That's all for extrinsic. So our goal is getting both intrinsic and extrinsic parameter. That is, in one sentence, camera calibration. I hope you are familiar with this slide. This is slide from lecture 3. So according to multivariate geometry theory, if we know camera intrinsic and extrinsic parameter and match a point across multiple viewpoints, then we can lift the multi-view observations to the 3D space. This is from lecture 3, last class maybe. And last class we studied this one. How can we get match a point across multiple viewpoints? Like how can we define some repeatable, consistent feature? How can we extract those features, and how can we make correspondence between them? That is about making matching between images. And another ingredient for 3D lifting is camera intrinsic and extrinsic parameter. We only learned the basic definition of them in maybe second class. And today we will learn how can we get this? How can we get intrinsic and extrinsic parameter? And that is camera calibration. I'm not sure you've seen this kind of checkerboard. This is what people typically do for the camera calibration. We have some big checkerboard, and people stand in front of the camera and then just rotate it in front of the camera. We just rotate the checkerboard in front of the camera. Then our automatic camera calibration algorithm give us some intrinsic and extrinsic parameter. But that is in very casual setup. Like if we have maybe 5 cameras, then we often do this kind of checkerboard-based camera calibration. Or in advanced setting, like if we have 100 cameras, then maybe let's say we are at hemisphere studio. All the hemispheres. I'm surrounded with the cameras. Back of me is camera, in front of me camera. Then holding checkerboard in front of some camera makes sense, but a camera behind me cannot see checkerboard. So what people typically do in this kind of hemisphere capture studio, people use this kind of 3D object. They make some 3D object, this kind of 3D object or some other shaped 3D object to calibrate cameras. So they just put this kind of 3D object in the hemisphere studio, and then camera calibration algorithm automatically give us intrinsic and extrinsic parameters. So this is for casual setup, and this is for some extensive setup. And So as I said, camera calibration is the process to determine the intrinsic. Intrinsic means, as I said, the K means K, we know K, right? K is focal point. This is K, right? Focal in XY and principal point in XY, this is K. And extrinsic, 3D rotation and 3D translation, parameters of a camera. For now, we will neglect the lens distortion. Actually, intrinsic includes distortion, but then we will simply neglect the lens distortion and see later how we can determine. The solution for KRT can be found by applying the perspective projection equation. We learned this, right? We learned this in camera Pinot model and perspective projection. So W represents our world coordinate system. So X, Y, Z are in world coordinate system, and U, V are in image coordinate system. So we first apply extrinsic parameter to transform the world coordinate system to camera coordinate system. And then we additionally apply intrinsic to convert camera coordinate system to image coordinate system. That becomes image coordinate system up to scale, lambda. And so there are two popular methods for camera calibration. Zeiss method uses a 3D object, and Zhang's method uses planar grids. We will study both approaches. The first one, Zeiss method, calibration from 3D object. This is, I showed you, right? I showed this kind of 3D object. This method was proposed in 1987, quite a long time ago, right? By Zeiss, and consists of measuring the 3D position of N, which is larger than 6 control points on a 3D calibration target, and the 2D coordinates of their projection in the image. So assumption is that we know 2D and 3D coordinates of control point. So the first thing we need to do when we try to follow Zeiss method is that we need to prepare this kind of 3D object. We can just do 3D print or other stuff to prepare this kind of 3D object. This kind of 3D object, and we need to know both 2D and 3D coordinates of control point. Control point is like some distinctive points, like a corner. So for the 2D, these blue points are control points. So for 2D, we can use image pre-processing method. We learned some corner detection algorithm in previous class, right? We can use any corner detection algorithms to detect this kind of corners. So the 2D position of this kind of corner can be obtained using image processing algorithms. And 3D, for 3D, we made this object by ourselves, right? We know actual size, we know actual rotation of this object, so we can actually directly measure the size and position of the corners, right? That is our assumption. So we prepare this kind of object, and we know all the physical size of this object. So we know actual size of 3D object and actual position of control point as well. So that is our assumption. For the 2D side, we use robust, good working image pre-processing algorithm to detect corners from images. And for the 3D, we know actual size of 3D object and actual position of control point as well. And now we are going to make a correspondence between 2D and 3D. That is very intuitive way, right? So when we design this kind of actual 3D object, this 2D detection algorithm should work robustly, right? So we need to prepare this kind of 3D object to have very simple patterns. I mean, if it has some complicated patterns, image pre-processing algorithms could fail to detect corners, right? So we need to make very easy, 2D image processing algorithm friendly 3D object. This 3D object, these patterns should be easily recognized by image processing algorithm, because in 2D space, of course, we can use manual notation. Let's say we have image, then we can manually select this kind of corner points, but this is too labor intensive, right? So we want some automatic algorithm. So we are going to use 2D pre-processing algorithm to detect corners. So that we need to design this kind of 3D object 2D algorithm friendly, easy to, consist of easy, simple patterns. Anyway, Zeiss method, in one sentence, a calibration from 3D object. Assumption is that For the 2D side, we use image processing algorithm to detect corners. The 3D side, we know actual size of 3D object and actual position of control point as well. And as I said, we simply apply this perspective projection. And this algorithm is called direct linear transform algorithm, in short, DLT algorithm. The idea of DLT is to rewrite the perspective projection equation as a homogeneous linear equation and solve it by standard method. So this is what we saw in previous slide, right? This is just a perspective projection between, relationship between world coordinate system and image coordinate system. RT is extrinsic and K is intrinsic, so that we can transform world to camera and camera to image. And we just, that's a simple math. That's the K can be rewritten like this, focal points and principal points. And this is RT, this is rotation matrix, and this is translation vector. That we can just apply the matrix multiplication to get this complicated matrix. And then, so we denote this complicated matrix with matrix M. So we can easily get this kind of M, and our goal is getting M, right? So because our assumption is that we know these 2D positions and 3D positions. As I said, 2D position can be obtained with image pre-processing algorithm, and 3D positions, we know actual size and actual position of the control point. That is our assumption. So our goal is getting matrix M. That is our goal. If we know matrix M and then decompose it to extrinsic and intrinsic, that's all. That's all we need to know. So our goal is getting M. And let's do some simple math, like we denote this matrix vector by capital P. And then by rearranging the terms, we obtain this kind of two equations. This is for x-axis. This is for y-axis in image coordinate system. As we have u and v, right? And this is just one example. We only have number 1, right? And here is index I. So this is just a equation for the first point. And we can, if we have n points, we can expand this equation to 2n row matrix. So we have 2n row matrix. And the rightmost term is 0 vector. And our goal is, so we know this matrix Q, right? Q is from here. It only consists of P, U, V. And assumption is that we know P, U, V. Assumption is that we know P, U, V, right? So this matrix Q is known. We know all elements in this matrix. X, Y, Z, W, U, V, all things are we know. 2D, as I said, U, V are from 2D image processing algorithm. X, Y, Z, W are from our actual measurements. So the Q is known, and our goal is getting M. And here we can rewrite this as a dot product between matrix Q and vector M needs to be 0. And our goal is, as I said, getting M, because we know matrix Q. So the minimal solution is that, so the dimension of Q is 2n times 12. There are 2n rows and 12 columns. As I said, here we have, for each point, we have x and y axis, so that we have 2n rows. And if you expand, there you can count. There are 12 columns, 1, 2, 3. There are 12 columns, right? And this is 2n. So Q is 2n times 12. And it should have rank 11 to have a unique non-zero solution M up to scale. Because each 3D to 2D point correspondence provide 2 independent equations. 2 independent means x and y. X and y equation. Then we only need 5 plus 0.5 point correspondence. This is just the rank divided by, we have 2 independent equations too, so that we have 5.5 point correspondences. Then we apply, we take integer, then we need in practice minimal solution is if we have 6-point correspondences, then we can get matrix M, right? What does mean the 6-point correspondences? As I said, let's get back to here. If we know like this point 1, 2, 3, 4, 5, 6, we only have 6-point correspondence. We have 6 2D positions and 6 points in 3D space. Then we can get matrix M. That is minimal solution. The minimal number of correspondence we need to know to get camera intrinsic and extrinsic parameters when you follow Zei's method is 6 points. The minimal number is 6 points. But in practice, there can be many noise. 2D pre-processing algorithm could fail. Our measurement can be noisy. There is no perfect stuff in engineering. So there can be always noise. This is different from theory. So in practice, we do not use only 6 points. In practice, we use more than 6 points over determined solution. So for n, which is larger than 6 points, a solution is least square solution, right? We can just apply optimization, which minimizes sum of squared residuals. Our goal is getting, we know matrix Q, and goal is getting matrix M. And we want some matrix M, which can make dot product between Q and M equals to 0. So we'd like to minimize the magnitude of QM using least square solution, subject to constraint where the norm of M equals to 1. It can be solved through a singular value decomposition. The solution is the eigenvector corresponding to the smallest eigenvalue of the matrix Q transpose Q, because it's the unit vector X that minimizes this norm of QX. The conclusion is that in theory, the minimal number of correspondence we need to know to get matrix M is 6. But in practice, there can be always noise. 2D estimated points can be noisy. Our 3D measurement could be noisy, so that in practice we do not use only 6 points. We usually have more than 6. Try to use more than 6 points, and that is over determined solution, so that we use least square solution, and we can use singular value decomposition to get matrix M here. That is DLT algorithm. Following Zei's method, we choose a 3D object to calibrate cameras. This derivation is simple, right? We just use perspective prediction and then do some simple math, and then it turns out that we know Q, noisy Q, and then our goal is getting M, which consists of intrinsic and extrinsic parameters. And then minimal solution is, if we have 6 points, that is minimal solution, but that is only in theory. In practice, we always have noise, so we use over-determined solution, more than 6 points, using least square solution. And of course, there can be some degenerate configurations, cases where DLT does not work. So as I said, our goal is getting vector M, which makes dot product between matrix Q and M equals to 0. And there can be like corner cases. So points lying on a plane or along a single line passing through a center of projection. These are separate cases. If we only have, let's say we have 6 points, but all 6 points are in the same ray, then it is not informative. If points are not sufficiently, or that is separate case, if all points are in the same plane, then if points are not sufficiently distributed in the 3D space, rank of M is not enough to get solutions. We need more points. And camera points on a twisted cubic, this kind of twisted cubic, that is also where DLT does not work. Points on a twisted cubic can be represented with polynomial equation, which can strongly limit rank of M. And applying direct, and yes. So these are corner cases where DAT does not work. And once we, so anyway, if we follow this approach, we can get matrix M. But we actually need, what we actually need is K and RT. Different, I mean, two different matrices. What we want is K and RT, not M actually. So we need to further decompose M into intrinsic matrix and extrinsic matrix actually. So once we have determined M, actually unfortunately, that is not the end. We need to do something more. We can recover the intrinsic and extrinsic parameters by remembering that M is a multiplication between intrinsic matrix and extrinsic matrix. And once we have determined M, we can recover the intrinsic and extrinsic parameters by remembering that. So this is just if we just apply matrix multiplication, we get this complicated matrix. Notice we are not enforcing the constraint that R is orthogonal. So actually, that is the definition of rotation matrix is two things. The first one is determinant of R equals to 1. Second one is that it is orthogonal. That is definition of rotation matrix. And rotation matrix should satisfy these two properties. So to enforce this kind of constraint, when decomposing M into two matrices, K and RT, we can use so-called QR factorization of M, which decomposes M into R, T, and upper triangle matrix K. QR factorization, to be honest, I can't remember it clearly, but I think you should learn in linear algebra class, I guess. This is just some decomposition method, which decompose a matrix into orthogonal and upper triangle matrix. I guess you learned this in linear algebra class. So we can use QR factorization of M so that we can get R, T, and upper triangle matrix, which is K. So that once we get M, we can try QR factorization or RQ factorization so that we can finally get K, RT. So that is, Zeiss method. A little bit complicated, but let me quickly summarize this again. So our goal is getting intrinsic and extrinsic parameters, and Zeiss method use 3D objects. So there are two approaches, 3D object and planar grid. Actually, this is Zeiss method, and this is Zhang's method. So the first thing we learned is this one, Zeiss method. And so our assumption is that we prepare 3D object, and we know actual size and actual position of control points. We have measurement, and then we use some off-the-shelf 2D image processing algorithm, like a corner detection algorithm, so that we can make correspondence between 2D and 3D. That is our assumption. And derivation is simple, right? We know this perspective projection, which consists of linear transformation. That is the reason why there is a linear. All the operations are in linear space. Direct linear transform, DLT algorithm. We just do simple math, and then we now reach to this slide. So there QM, where Q only consists of known variable, world coordinate system, position world coordinate system, and position image coordinate system, which has a dimension of 2n times 12, and our goal is getting M. Q is known, M is unknown. And minimal solution to get M, the number of minimal correspondences, 6 points, because the rank of Q is 11 up to scale, so that, and each correspondence give us two independent equations, X and Y, so that we need at least 5.5 points. Taking integer, we need 6 correspondences in theory, but in practice, there is always noise. So we need to use overdetermined solution, like a least square solution, and it turns out that we can just simply use singular value decomposition to get matrix M. And these are some corner cases where DIT does not work. And once we get M, we need to decompose it to K and RT. And then fortunately, we have QR or RQ factorization, which I hope you learned this in linear algebra class, so that we can decompose M, we can further decompose M into K and RT, where R is orthogonal matrix and K is upper triangle matrix, so that we can get K and RT. And this is example of Zeiss calibration result. So there are some notations. So alpha U and alpha V are focal lengths in intrinsic, and skew parameter is like the K actually looks like K and U 0, alpha V, V 0. So we have skew parameter here. So the alpha U and alpha V are focal lengths, and U0 and V0 are principal points, and skew parameter is here. And this is Zeiss calibration result. So alpha U is focal length. It has some large number, like 1.6K. And alpha U divided by alpha V, it should be actually almost the same. It should be, it should be 1. And it's quite close to 1, right? And this is skew parameter. But in practice, skew parameter should be very small. It's too large. It should be very close to 0. So that means that our initial Zeiss calibration result is not very good. K is too large. And U0 and V0 are principal points. These are image center. So from this numbers, we can guess that our image shape, height and width will be, width might be 760 and height might be 710 maybe. This is close to image center. And average reproduction error, we will learn reproduction error in the next line, but average reproduction error is quite low. So the error is small, but the problem is that this is too large. Skew parameter should be very close to 0. So there is something wrong. There is something wrong in Zeiss calibration results. So we need to actually do further things. And recommendation, as I said, is that we use many more than 6 points, ideally more than 20 points, and non-coplanar. Coplanar means all points on the same plane. And recommendation is, as I said, if you use only 6 points, then you won't get good calibration result. Because, as I said, this is just a theoretic minimal number of correspondence. We need more than 6 points because there can be always noise. So anyway, this is initial Zeiss calibration results. Focal length ratio makes sense, and this image center principal point makes sense. But then the problem is that skew parameter is too large. Average reproduction error makes sense, but this is problem. And let's learn the reproduction error. So the reproduction error is just the Euclidean distance in pixels between observed image point and the corresponding 3D point reprojected onto the camera frame. So observed image point means our assumption is that we know 2D and 3D points, right? Observed image point is from image pre-processing algorithm. Like we can use corner detection algorithm, so anything to that the observed image point position that we used for the initial Zeiss method, and corresponding 3D point reprojected on the camera frame. So from this initial calibration, we know all the camera parameters. Intrinsic, all we know, right? So that we have, our assumption is that we know U, V in image, and word, X, W, Y, W, C, W. These are our assumptions. We know this, right? And the observed image point are this one, UV. And we know X, W, Y, W, Z, W in word coordinate system. And we know extrinsic and intrinsic, right? So then we can convert this word coordinate system to camera coordinate system. And then we can further transform the transformed camera coordinate system to image coordinate system. Then we can measure pixel distance between this one and let's denote by U prime V prime. We can, measure distance between UV from image pre-processing algorithm and UV from projection, right? This is actually reprojection error. Ideally, this should be very small. You understand? Is it good? Our goal is minimizing the reprojection error. And the reprojection error gives us quantitative measure of the accuracy of the calibration. Ideally, as I said, it should be 0. But this assumption is that this is accurate. Assumption is that this should be accurate. If this is not accurate, then nothing works. So our assumption is that this is accurate. Assuming this is accurate, our goal is minimizing reproduction error. So this is, I guess, from initial size method. The blue ones are from, as I said, image processing algorithm. We detect corners. The control point looks reasonable, but as you can see, reprojective points, we have PWI, points in world coordinate system, and we know intrinsic and extrinsic parameters that we get from initial size method, and then we reproject it. This is as a reprojection function. And this is, the red ones are reprojected point. As you can see, there is a severe difference between blue points and red points. In theory, actually, DLT should work. In theory, if we have, if we have 6 perfect correspondence and DLT is based on perspective projection, then it should work, right? But in practice, unfortunately, it does not work. There are many, because there are many assumptions. The first one is obviously there should be no noise, but there is always noise. Our measurements, as I said, observe 2D points, they can be always noise, and we actually exclude lens distortion in intrinsic, and errors in corner detections, least square optimization is prone to noise. All the stuff makes DLT not a perfect solution. In theory, it needs to be perfect, but in practice, it does not. It is not. So we further do nonlinear calibration. So in DLT, from its name, we can know that it's a linear transformation, right? But we are going to do nonlinear calibration refinement based on initial DLT's output. It is, it is not very good, but reasonably makes sense. Somehow close to, distance between red and blue is not very large. So given we have some reasonable initial calibration result from Zeiss method, we are going to further try nonlinear calibration refinement. As I said, the objective function is minimizing distance between blue and red points. The calibration parameters, KRT, determined by DLT. This is initial camera parameters, right? Can be refined by minimizing following cost or objective function. Argmin, where objective function is minimizing distance between blue points and red points. That is our objective function. And we also include lens distortion now. And it can be minimized using Lavenberg, Marquardt, or more robust than Gauss-Newton to local minima. Of course, you can use a stochastic gradient descent or other things. Maybe you are familiar with SGD more than this kind of Lavan. Actually, I neither familiar with this kind of stuff. But SGD is a first order optimization. First order, and these ones are second order. They use Hessian. It is based on Jacobian. So it is more robust to, in particular, we only have like maybe 20 points, very small data. So if we have very small data, we need some robust optimization technique. And these are very robust to noise. SGD, widely used for neural network training. We have lots of parameters, right? Lots of parameters, lots of data. So the network is very robust to noise, although we only use SGD. So when training neural network, we can use SGD. But if we have very small amount of data and very it might be very prone to noise, then we need to use Hessian-based second-order optimization, Lavenberg, Marquardt, and Gaussian-Newton. Anyway, detailed name is not important. So the important thing is that we get initial camera parameters from Zeiss method based on DLT algorithm, but because of noise and lens distortion, all those stuff, it makes a little bit not accurate. So you can see discrepancy between blue and red point. So we are trying to further refine camera parameters using nonlinear calibration refinement by minimizing this objective function. And if we keep optimizing, as you can see, getting better, right? This is initial, next, getting better, right? And here, the distance between blue and red is very small. So that means our reproduction error is very small, so that our camera parameter, combination of KRT, lens distortion, can explain this kind of our prepared correspondence between 3D and 2D points. So that finally, we can get all the stuff. We can get KRT lens distortion way better than initial calibration results, only based on DLT method. So that is the reason why we further apply nonlinear calibration refinement. So it makes sense. I guess it's not very complicated. Once we get KRT from Zeiss method based on a direct linear transformation, from its name we can know that it's linear. There's many approximations and assumptions, like there can be noise and lens distortion is not included for the initial calibration. So in the second stage, we introduce lens distortion, and we use actual reproduction error to further refine the initial calibration, so that we can get way better calibration result than initial Zeiss method. This two-stage approach is based on Zeiss approach. And all this step, back to the initial point. All we need to know is 2D and 3D points. 2D points from image processing algorithm and 3D from our measurement. Once we know only these two points and correspondence, then we can apply first stage and second stage automatically, so that we can get KRT. There's no manual effort for humans. All the algorithm is automatic. That was Zeiss method. And let's see the other approach, Gyeongsik algorithm. So Zeiss method is a little bit advanced one. We need to prepare a 3D object. It is a little bit annoying to prepare this kind of 3D object. So this is more like easy to try. We do not need to prepare a 3D object. We only need to prepare this kind of checkerboard. Let's say we have this size of checkerboard, and then we just hold this in front of the camera and then just rotate it. That's all. The Zeiss calibration requires that world 3D points are non-coplanar. That means, coplanar means all points are in the same plane, and non-coplanar means, all points are not on the same plane, which is not very practical. As I said, we need to prepare this kind of 3D object. Making this 3D object is also not very trivial. So today's camera calibration toolboxes like MATLAB, OpenCV use multiple views of a planar grid, checkerboard. They are based on method developed in 2000 by Zhang, Microsoft Research. So Zeiss calibration requires that the world 3D points are non-coplanar, which is not planar vertical. Oh, and this figure shows the example of Zhang's algorithm. The basic strategy is almost the same, because we assume that we know actual size of checkerboard, we know actual position of points on the checkerboard, and that the assumption is that we can easily get corner points on the 2D image space using image pre-processing algorithm. That is the assumption. So the basic strategy is almost the same, but makes it more casually, instead of making requiring 3D object, non-coplanar 3D object, we can use just a plain checkerboard and then just rotate it in front of the camera. So it makes us easy to use. And so as I said, the basic strategy is almost the same. As in Zhai's method, we start by writing the perspective projection equation. Again, we neglect the radial distortion. Our Zhang's method, the points are all coplanar, right? We only use plane shape checkerboard. So the ZW could be 0. Z coordinate in world coordinate. Z coordinate in world coordinate system could be 0, and thus we can rewrite like this. And the other things are the same, just the same thing in Zhai's method. All the things are same, so that K can be rewritten like this. This is RT, and then instead of M, we are now trying to use H. And this matrix is called homography. We learned homography, right? I'm not sure you can remember it. Homography is the most complicated transformation in 2D space, right? So that, and doing the same thing. So now it's almost the same. Instead of matrix M, we are now going to use matrix H. And here is yes, so we have these kind of two equations, and then we can rewrite this in matrix vector multiplication. As I said, Q is known. We know our assumption is that, as I said, the assumption is almost the same. Our assumption is that we know 2D points in the image space using image preprocessing method, like a corner detection algorithm. And then 3D, we actually know the actual size and actual position of 30 points on the checkerboard. That is assumption, so that we know matrix Q, and our goal is getting matrix H. So, and difference from Zhai's method is that M was, the shape was, M was 2n times 12, right? But H, now the number of column is 9, not 12, because our assumption is that all the points are on the same plane, all the same plane, so that it reduced from 12 to 9. Should have rank 8 to have a unique non-trivial solution H. The same thing, and each point correspondence provide two independent equations for x and y. So 8 divided by 2 is 4, so we need 4 non-collinear points. That is minimal solution, minimal required number of correspondence when we try Zhang's method. Because rank of Q is 8. So, and each correspondence give us two independent equations, x and y. So 8 divided by 2, we need 4 non-collinear points. That is minimum number of correspondence to try Zhang's method. But as I said, as in Zhai's method, this is only theory. There can be always noise. So we need to try over-determined solution, more than 4 points. It can be solved through singular value decomposition, same considerations as before. And then H. So once we get H, using this kind of singular value decomposition, as I said, if we have only 4 points, we can just do this simple math to get H. But then, as I say, in practice, we often try over-determined solution and use SVD. We can try anything, so that once we get H, we need to decompose it to KRT, right? We need to decompose H into KRT, right? H can be decomposed by recalling that this one upper triangle matrix and rotation matrix and translation vector. Different from Zhai's, the decomposition of H into KRT requires at least 2 views. So in Zhai's method, if we have M, then we can try QR factorization to get KRT. But different from Zhai's method, decomposition of H into KRT requires at least 2 viewpoints. So in practice, actually, the more views, the better. This is just a, theoretic minimal number of viewpoints. In practice, the more views, the better. 20 to 50 views spanning the entire field of view of the camera for the best calibration result. Notice that each view J has a different homography HJ, right? And so different R and J. However, K is the same for all views. K is intrinsic, right? I mean, K is intrinsic, so I mean, assuming we do not change the zooming or image size resolution, K remains constant across different viewpoints. Different viewpoint, K is the same, but H could be different because, I mean, if we change the viewpoint of the checkerboard, then that is equivalent to changing camera R and T, assuming we are standing in front of camera. So for each viewpoint, we have different HJ, so different RJ and TJ. However, K is the same. So for each viewpoint, we have constant K, constant intrinsic, but different extrinsic. And this one is also similar. In theory, we only need 2 views, but in practice, the more views, the better. So like about about 5 minutes, we just hold the checkerboard and then rotate in front of the camera to secure enough number of viewpoints. That is what we do when doing camera calibration. So these are very complicated. Details won't be asked at the exam, but you can just read this if you're interested in how can we get KRT from H from multiple viewpoints. As I said, once we getting H is very similar to Zhang's method. Just if we have 4 points, that is minimal solution, we can get H. Or if we have more than 4 points, we can use SVD. That is very similar to Zhang's method. And then decomposing, in case of Zhang's method, decomposing M into KRT is just a QR factorization. But Zhang's method, we need multiple viewpoints. That is about this one. How can we get KRT from H from multiple viewpoints? Very complicated. You do not have to memorize all the details, but I encourage you to understand what is happening in this process and how can we get KRT from H. And as I said, this is homography transformation. Homography is, simulating multi-view observations in 2D space. That is, in one sentence, homography. If we know 3D shape of this one, let's say this is 3D shape, then maybe we can see unseen viewpoint, unseen face of this rectangular, right? This cubic, right? Let's say this one A, B. This is C, D. If we rotate 3D object, then we can see some unseen face. We only see A, B, but if we rotate it, we can see C or D, C, D. But that is 3D rotation. That is 3D rotation and translation. Homography is in 2D transformation. So it tries to simulate. Assuming we don't have any new observations, we only simulate these viewpoint changes in 2D space. That is homographic transformation, and that is H. That is H. Once we have H, we need to decompose it to KRT, and H is homographic transformation matrix. So we studied Zhai's method and Zhang's method for the camera calibration. Okay, is it good? Not very complicated? Anything unclear is okay? Then let's proceed to camera localization. So you need to see, I think you need to see this first. Camera calibration, camera localization is getting extrinsic while intrinsic are given. So camera calibration, like Zhai's method or Zhang's method, our goal was getting both intrinsic and extrinsic, right? Both intrinsic and extrinsic, right? But camera localization, the goal is our assumption is that we already know intrinsic. Now how can we get extrinsic? That is our goal. That is called camera calibration. So it's like a subset of camera calibration. Camera calibration getting intrinsic, both intrinsic and extrinsic were the goal of camera calibration, but the camera localization only getting camera extrinsic, while intrinsic is given, is the goal of camera localization. So this is the problem of determining 6 degree of freedom. So DOF is degree of freedom. Degree of freedom. Pose of a camera, position 3, orientation 3. So we have 6 degree of freedom of a camera. We can change camera position. We can change rotation of camera. So we have 6 degree of freedom, right? Respect to the word frame from a set of 3D to 2D point correspondences. And assume the camera to be already calibrated. Already calibrated means assumption is that we know intrinsic is given. And DLT can be used to solve this problem, but it's suboptimal. So we want to study algebraic solution to the problem. So for the camera localization, whose goal is getting camera extrinsic, while intrinsic is given. So in previous Zhai's and Zhang's method, we studied the minimum number of points, right? Zhai's was 6 and Zhang 4 to get both extrinsic and intrinsic. But here we only interested in camera extrinsic. And what is the minimum points? How many points are enough? So the assumption is also the same. We know 2D and 3D points, and we have correspondence. That means that the matching is done. And so, for example, 2 points means we know 3D and 2D position of a point A, and 3D and 2D points of position of point B. And the conclusion is here. If we have only 1 point, there are infinite solutions. It doesn't make sense. If we have 2 points, infinitely many solutions, but bounded. If we have 3 points, assuming they are not on the same linear line, then we have up to 4 solutions, and we have 4 points, unique solution. So for the camera localization, we only interested in camera extrinsic, then 4 points makes unique solution. Let's see the reason. So we have only 1 point. 1 point means we have some world coordinate system. 3D point is here, and we have image plane here. There can be infinite camera rotation and translation. For example, we can. How can I? Maybe. I can't. Sorry, I can't. Maybe. No. So this is image, and I'm not sure, but anyway, if this is camera, there can be infinite number of camera rotation translation that have this kind of image plane observation and 3D observation. We can make, arbitrary radius, arbitrarily rotation of camera on the sphere, 3D sphere, right? So there can be infinite solutions for camera rotation translation. And 2 points, infinite solution but bounded. We can change rotation translation of camera to explain this image coordinate system observation and world coordinate system observation. But so it's bounded, but infinite solution. This is bounded. And 3 points. This is called P3P problem. 3 points, assuming they are not on the same line, up to 4 solutions. So as I said, this is high school math. I remember this is second law of cosine. When I was a high school student, I learned this is second law in cosine. I'm not sure these days term. Anyway, so we have, let's say the length of AB. Length of AB is here. S1 is here, right? And LB, LA, these are here. The lengths between length between points and camera. LA, LB, LC we have here. So we have these ones, and from this equation, as we know, A, B, C, 3D points are given. So we know this length. This is unknown. This is unknown, unknown, unknown. Cosine AB. Cosine AB can be, we can know this because we have image coordinate system observation. So we can get cosine between A and B. So this is given. So what we do not know is only lengths, LA, AB, LC. This is the same. So LA, AB, LC are unknown variables from these three equations. And it is known that n independent polynomial equations in n unknowns can have no more than solutions and the product of their respective degrees. Thus the system can have maximum of 2.2.2, 2 times 2 times 2, which is equals to 8 solutions. Because every term in the system is either a constant or a second degree. So they are second degree, right? For every real positive solution, as I said, we're interested in LA, LB, C with the lengths, so they need to be positive. So we exclude negative. Then out of 8 solutions, we only have 4 valid positive solutions. So that is the reason why if we have only 3 points in world coordinate system, image coordinate system, there are 4 valid solutions. And then by defining x equals to this one, it can be shown that system can be reduced to 4th order equation like this, at 4 point, and then so we have 4 solutions, right? 4 possible solutions, and out of these 4 possible solutions, we only need to get a unique R and T. That is our goal. So that what people typically do is introducing additional point, 4th point. Because in real world, we have more than 3 points. In real world, we have many points. So we use additional points to validate. We have 4 solutions. And we introduce additional 4th points to get some solution out of here, which is the minimal errors. So that we introduce 4th point. We introduce a 4th point. 4th point can be used to disambiguate the solutions. The classification of the 4 solutions and the determination of R and T from the point distances was given Gauss algorithm implemented OpenCV. So assuming we have 3 points, we can get 4 possible solutions. And out of 4 possible solutions, we introduce, so there are many complicated numbers. Let me clarify this one. We have 4 points. We have 3 points. We have 3 points in both 2D and 3D. And then based on this Carnot's theorem, we have 4 valid solutions, 4 candidates. Out of these 4 candidates, actually we only had 3 points, but we introduced additional points, 4th point, to get unique R and T out of these 4 points, 4 solutions. So there are many 3 and 4, but each 4 and 3 are different. Initially, we have 3 points, but so that we have 4 possible solutions. Out of these 4 possible solutions, we introduce 4th point to get unique R and T, best R and T. So this is actually, so modern solution to P3P is different. So the unknown variable in this slide was LA, LB, and C, right? Our interest was LA, LB, and C, but modern approach is based on camera orientation, not length. You do not have to remember all these details, but modern solution uses different strategy. And if we have more than 4 points, then we can use more points. The previous strategy was using 3 points to get 4 valid solutions and pick the best one by introducing additional points. But what if we can just use many points at the initial stage? That is possible. That is called. But if we have more and more points, the operation becomes heavier and heavier. So that is the reason why we're trying to restrict the number of points to 3 and then use additional points. So that is, if we have more than 4 points, ePMP, efficient PMP algorithm can be used. You don't have to remember details, but this is what is happening, and we have more than 4 points. So that we learn camera localization, whose goal is getting camera extrinsic, and the typical application is SLAM, simultaneous localization mapping. In autonomous driving, or robot vacuum cleaner, from its name, we can know that it makes localization and mapping at the same time. Assuming we do not have any map, it makes map and localizing itself at the same time. So that is SLAM, autonomous driving, and robot vacuum cleaner, they do SLAM. And all PMP problems solved by DLT, ePMP, or P3P algorithm prone to errors. Is that there can be always errors and noise. So we use Randstad algorithm. We haven't learned this, but we use Randstad algorithm to remove the outliers. And the conclusion is that if a camera is calibrated, both DLT and ePMP can be used, right? But when intrinsic is given, we can try both ePMP and DLT, but the result is that ePMP is way better. ePMP is more than up to 10 times more accurate and more efficient than DLT. So that is the reason why we are interested in ePMP. As you can see, error significantly lower than DLT. Here ePMP, error is much lower than DLT, and computation time much lower than DLT. So ePMP is way more accurate and way more efficient than DLT. That is recap. So if we have calibrated camera, then that means intrinsic are given, then we can use DLT and ePMP. Uncalibrated cameras, nothing is known, then only DLT can be used. Of course, we can try further nonlinear refinement. ePMP, minimum number is 3, but we use additional 1 to get best solution out of 4 possible solutions. DLT, 4 if coplanar, Zhang's method. 6 if non-coplanar, Zhai's method. And both output of DLT and ePMP can be refined by nonlinear optimization by minimizing the sum of square reproduction errors. Let me show some real-world cases. So when I was in Meta, I made this kind of small casual capture setups. Like this is Microsoft Kinect. The camera is Kinect. There are maybe 5 to 6 cameras. This is 3 cameras. I hold the checkerboard and then rotate myself in front of the camera to calibrate cameras. Not sure if the video is. This was me, and I want to show the video. I can't play video, but in front of this capture setup, there was a wristband, EMG wristband, which can read electronic signal from brain to hand muscle. So I synchronized this EMG wristband and cameras to get some hand pose. But in real world cases, there was very casual setup, like a 5 to 6 cameras, very casual setup. But in Capture Studio, we may have over 100 cameras, and that is not trivial in this expert level engineering and techniques. And for each capture, we calibrate cameras for each capture because temperature and humidity changes, so calibration changes. It's very small amount of calibration change makes the huge 3D and 2D errors. So we need to calibrate again and again for each capture. This is Moxie Studio in Meta. I wanted to show the. And another thing is that we didn't take care about the synchronization, but unfortunately, synchronization is also not very trivial. Synchronization means all the camera needs to take images at the same time. If we have multiple cameras, they need to capture images at the same time. So what people typically do, tricky way is clap. Let's say we have microphone and multiple cameras. Then we do clap. Then there's a strong spike on the audio signal, and then for all cameras, we can see I'm clapping, so that we can synchronize all the cameras. We do not need the microphone. So if we have multiple cameras, then we do clap, then all the cameras can see I'm clapping at the same time, then we can synchronize cameras. That is how broadcasting, producers do. They have some slate, right? Slate, they slate. Slate, they do slate because they need to synchronize cameras, right? Synchronize cameras and microphone. When making some content, they need to synchronize cameras and microphone. So they use slate to make a strong spike at the audio signal and visual signal as well to make a synchronization. Advanced way is using synchronized triggers. This is synchronizing triggers. You can use this kind of ones for this setup. Of course, we do not use clap for this advanced setup. We use this kind of trigger system. But in casual setup, then we can just use clap to synchronize cameras or synchronize camera and microphone. Okay, that's the end, and let's check the attendance and finish. Thank you.